For more information, please visit our website at DarkCybernetics.com. This is DarkCybernetics, Data Structures, Stacks and Queues. Follow along with our free course documentation. In this video, we'll discuss the difference between stacks and queues, and we can define a stack or a queue as a linear data structure or a linear container. Here in this video, we will discuss the operations performed by the stack and the operations performed by the object we call the queue. The definition we can give for a stack is that it is a linear container of objects. These objects could be data members, they could be items, it could be a list of a grocery list or other pieces of information we wish to store. Also in this video we will discuss the idea of being linear and some of the more basic ideas such as what we refer to as first in first out, or FIFO, and LIFO was last in first out. So these two data structures, these are abstract data structures, and for the stack we do last in first out. The last item we place on the stack is the first item we pull off the stack, and for the queue the first item we put in the stack is the first item off the stack. So last one in the stack for first one off, and for the first one in is the last one out. Alright, there is another piece of information here. These are ADTs, or abstract data types. An abstract data type, as we talked about in previous videos, is a mathematical model or a logical description of information. This, of course, there is math, and these data structures here are, the stack at least is considered recursive. I mean, it depends on the previous information. Let's see. Well, also we can talk about what other feature in SDL, not SDL, but the operations for the stack are, of course, push, right? And if we push onto the stack, we are, of course, adding an item, and we can write that here. We are adding to the stack. Alright, so the next operation is, of course, pop. When you pop off of the stack, we are removing an item from the stack. Okay. And then there's another operation, or top or peek. And if we peek at the stack, we are just looking at the top element to return the top element. It's also referred to as top. And we take a look at the first element, so we're going to return the first element. Alright. There's another operation we can perform, is we can see is the stack empty. So is empty. It's also another operation we can perform on the stack. And to see is it empty, it is a true or false statement. It's a Boolean, which is a yes or no value, 1 or 0. And to see is the stack empty or not. So if it is true or false. Alright. If it's true, we're going to return true. Alright. And for the queue data structure, it has two operations. And those operations are enqueue and dequeue. When we enqueue an item, we are doing what? We're placing an object at the end of the queue. So we're at enqueue here. And so we're placing an item at the end of the queue. We're going to, of course, insert at the end, or the back of the, insert at the back part. All right, and we dequeue. If inserting is adding to the queue, dequeue means we have to remove from the queue. Okay, and now since we've you talked about the stack, which is a last in first out data structure, and we talked about the queue, which is a first in first out data structure, we'll talk about the complexity, or the amount of time required for each operation. Adding, okay, we can also return the size, right? And each one of these things requires a constant amount of time. We're talking about the number of operations for each activity. All right, so to push to the stack, it requires constant time, one operation. Removing from the stack requires one operation for a stack. Checking for an item, the top item, it takes a constant amount of time. And to see is it empty, it takes generally a constant amount of time if you know how many elements is in the stack. And the same can be said for the enqueue, dequeue, and size operations for the queue data structure. Whereas O of 1, which is constant time. And we will get into complexity class and performance analysis later. But for now, we will say that each operation for the stack and queue occur in constant time, unless we are talking about searching. If we search for in an unknown area, we would need to, at worst case, look for or search through all the elements in the stack, or all the items or objects in the queue, which would take, of course, n times the number of items in the stack. For each one of these data structures, they perform several operations, and they're used for specific tasks. The stack, for example, has, let's see, this uses a good example here. The stack is generally used for mazes, and when we think about mazes, we need to return the goal state and the start node in the goal state. So we can use this as more efficient for returning the last in first out. Think about that. We are talking about we need for a backtracking algorithm or for a maze, and we think about using the queue, and we implement, we'll use the queues to implement other data structures such as the linked list, which we may get into later. But we can use those along with the queue structure for breadth first search for tree search algorithms. Tree search here. And items like the BFS and DFS, which is the breadth first search, and the depth first search, which is, of course, a graph algorithm. Right now we're talking about linear data structures, so we will not go into that as of yet. But we need to return some type of stack, so we want to hold the closest nodes or closest areas, and so we won't hold all the state space, which is generally a topic we generally cover in artificial intelligence. But also for the stack data structure, we can parse, and parsing is generally used for text, and we can do other operations such as evaluate expressions, or we can do expression conversions, and by way of prefix, postfix, and infix conversion, where we convert values from infix to prefix, prefix to postfix, and so forth. So I'm going to abbreviate here, prefix, and I'll make a slash here, and then I can say postfix, and then I'll say infix. Okay. So we've talked about the stack as the last in, first out abstract data type, and talked about the queue as the first in, first out data structure. And each one of the operations occur in constant time. And for the queue data structure, we can enqueue, dequeue, and call size. All right, so let's move along. And let's erase, well, delete. That's the best way to describe it. You need to delete information when we talk about data structures. And let's move on to something a bit more. Let's draw a picture of what we call a stack. And let's suppose these were pancakes. And suppose you had a plate and we put, let's just write the word stack up here. Okay. So it has three operations. If we place items on the stack, this is push, right? And which is constant time. We take item off the stack, it is pop. And if we check the first item, it is peak or top. So let's draw a red line to that. Alright, so let's label it. So this is peak, it's two E's. That's P-E-E-K, I think. Alright, this is supposed to be pop. And this other arrow is supposed to be push. Okay. Alright, so for a stack of push, pop, and peak. Alright, we're going to line stack here. And let's talk about the other data structure, the queue. Q-U-E. Alright, let's draw an example of the queue. Of the queue data structure, we will think about it this way. It looks almost like an array, but we have a head and a tail part of the structure. So, but we give them different names. The head is referred to as the front. So right front, we want to write the word front here. And the back part is called the tail. And we use the word rear here. Alright, so for the stack we can push, pop, and peak, and for identifying portions of the notice that, well, for the queue, the head may not always be here. The head may not always be there, but since items are added and removed from the queue and from the stack. So in some data structures, you may want to keep a notice of where is the head and where is the tail, especially for data structures like the linked list. You may want to keep these things really on memory. And when we search these data structures, as we said before, it takes place in O of n times, which is the number of operations, the number of the elements. And we will get into complexity later. Okay, so we have a stack, and we have the queue, and search takes O of n op times. Okay. So let's look at the algorithm, which is a logical process. Well, we can describe an algorithm as a logical step-by-step problem for solving a problem in a finite amount of time in legal computational steps. So we need to assign legal computational steps for the push operation. Here in this algorithm, we simply check to see, alright, we can say that we check to see, well, we'll check to see if the data structure is full or not. We'll check to see if it is full, right? Because we're pushing an item onto the stack, and if it is full, we print an error, okay, and then we exit. Alright, that makes sense. If we try to push an item onto a stack that is full, and we should return an error. And if it is not full, let's write that down here. We need to use a lot of times an incremental operator, or have a variable that we increase the value to. So we want to increment the counter for the variable we use to denote the size or the amount of items inside of the stack. So we write we're going to increment the counter. Okay. And we're going to increment the counter to denote that we added to the elements. Alright. Seems simple enough. So if we're pushing on to the stack, we need to check to see if it is full. I want to print an error and then exit if it's already full. If it's not full, we're going to increment the counter and then add to the elements. Alright, so let's look at the other operation called pop. And in this case, since we are taking items off of the stack, the instructions are a bit simple, well, a bit different. We need to check to see if it is, of course, not this time. So we're going to check to see if it is not full, or not empty. Right? And then, and if the stack is empty, we want to print an error. Okay. So for our first operation for pop, we're going to check to see if it is empty. And our next will be, if the stack is empty, we need to print an error message and return exit. And then finally, we want to check if it is not empty, then we want to print the top. And then increment, or decrement. Since we're taking off the stack this time, we want to, since we check to see if it was not empty, we print at the top and then we decrement it. So we reduce the amount of elements in in stack. Alright, that seems simple. So first we check to see if it was full. If it's not full, we print an error. And if it's not full, we increment the counter to add to the element. And we do the reverse for pop. Let's move on. This time we'll look at some other operations. So we have the queue. Let's look at some applications for the data structure called the queue. Alright, so let's start on this side. Alright. These are some applications for the queue. Well, the queue data structures, we can do real-time, generally used for real-time systems. Some of those real-time systems are those involving suppose we had what's a real-time system? Something like a phone, where we could interrupt to operate a continuous stream of requests. We get phone calls. There's always a stack of phone calls coming in. We can think about this the same as we do interrupts for our CPU, for a central processing unit for job requests. We handle interrupts for CPU. Write that down here. CPU tasks. Okay. And requests. What are requests? Well, the type of request, shared resource requests. Okay. So we talk about phone calls, you talk about real-time system applications for interrupts for CPU tasks and handling shared resource requests. Okay, so those are good examples this time, since we are using a queue. And let's think about that. We have phone calls. Since there's a continuous stream of phone calls, the queue, we can take things on and off. We can enqueue and dequeue requests for calls. And we can also, let's write something down here. Let's say that the arrays, well, one benefit of using arrays are random access. And as we know which element, that's a random access data structure, right? For an array, we've talked about arrays before. Arrays are random access. And other data structures like linked lists have to traverse information sequentially. Let's write that down here in the block. So we access this information in a sequence, or sequential, meaning number by number, or file by file, record by record. And of course, if we access information sequentially, it means it takes the number of times, or even if we had to resort the items in the list, it would take n times. But random access takes constant time. Okay. In C++, when we use an object for a queue, we use push and pop. We just need to define an object in C++ So if we had an object called stack, and we called it the stack, we gave it some kind of object name, which we just need to say something. You could even say stack again, but we just called it R. We use the dot operator, and we call peak, or we call pop, by just having it saying the word peak, since they are reserved words. And we just put a value in here. If we want to pop an item, we'd say R dot pop, or if we want to remove an item, we'd say R dot push. We can put the numeric value and the parameters. Okay, this is for C++. It's a different, similar implementation for using something like Java or C. If the enqueue, dequeue are not available, you have to actually define your own peak and pop function. And these are keywords, since they are reserved words in the C++ language. And these are objects. This R is an object. And so we talked about using stacks and queues in this video. And for more information, please visit our website at DarkCybernetics.com.